For the final session of the S.T.E.M.S lecture series, we have Anant Mudgal with us.
He's a B.Sc student at CMI and has represented India at the International Maths Olympiad on 4 occasions, and he has multiple medals in the bag. Now he'll be talking to us about counting with bijections, innovative ways to count, and so I invite Anant to start his talk.
Hello everyone. So today we'll be talking about some basic counting principles, and okay, let's start the discussion. So I assume you're familiar with addition and multiplication principles, but let's review that. So suppose we have a set A with m elements and a set B with n elements, and we want to pick one element from either of them. Then the number of ways to do this is clearly m plus n, right? Because you can pick one of these m or one of these n. Similarly, we have the multiplication principle. So if you want to pick a pair of elements, one from A and one from B, then the number of ways of doing so is m into n, right? So these are basic counting principles. Now we'll talk about some more abstract idea here. So the idea is this. Suppose we want to count the number of elements in some set A. Oh, and before that, let's also recap a little bit of binomial coefficients. So suppose you have n objects, and our goal is to select k objects out of these. So we denote the number of ways of doing this by n choose k, and we also have a formula for n choose k. So I guess you're familiar with that, but let's recount that. So the formula is so we also know it in the form n factorial divided by n minus k factorial times k factorial, right? So okay, so let's resketch this argument. So okay. So suppose you have n objects and you want to pick k objects out of these. So you can pick the first object in n ways, right? Because there are n total objects. For the second object, you have n minus 1 choices, right? Because there are n minus 1 remaining objects. Similarly, for the third object, you have n minus 2 choices because there are n minus 2 remaining objects. And continuing in this fashion, we get that the kth object will have n minus k plus 1 choices. So apparently this looks like the number we are looking for. But turns out that any selection of k objects, so you have k objects x1 dot 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 xk, right? These k objects could be in, we could have chosen these k objects in their rearrangements. And so how many rearrangements are there for these k objects? So we count that. We show that this is a fixed number irrespective of which k objects these are. So then you can see that whatever that fixed number m is, the result will be this divided by m, right? So we find that number m. Now for any rearrangement, we can pick one object in k ways, the second one in k minus 1 ways because there are k minus 1 objects left, and so on, similar to this argument, and we get this. So our result will be like this. Oh, also let's just clarify. So by n factorial, we mean n times n minus 1 times so on till 2 and 1. So product of all natural numbers up to n. So I guess it's clear. Okay, let's move on. So I'd like to highlight another proof of the n choose k formula. So this is a more innovative proof. Like the proof we saw just now is rather standard. Suppose you have n people in some conference, and you want to pick a committee of k people out of these, and among the committee members, you want to select one chairman. So this is our counting problem, let's say. Now, the number of ways of selecting a committee out of n people will be n choose k, right? Because we are choosing k people. Now, from this committee, we can choose the chairman in k ways, right? Because there are k people, we can assign any of them to be the chairman. So we have also k choose one is just a fancy way of saying k. Now, this is one way of counting this object. We'll present another counting method, and from that we try to obtain some information. So instead of selecting the committee beforehand, what we do is we select the chairman. So there are n people, and we select the chairman. So there are n ways of doing it, right? So we have n ways of selecting the chairman. Now there are n minus 1 people that remain, and from those n minus 1 people, we have to choose k minus 1 people to fill the remaining committee. So we have n times n minus 1 choose k minus 1, right? And since we are counting the same thing, these two things are equal, right? So we have k n choose k equals n minus 1 choose k minus 1. So we don't know what these n choose k, n minus 1 choose k minus 1 mean, but we know there's some relation between them. And we'll proceed along these lines to get a formula for n choose k. So we know that n choose k is n over k times n minus 1 choose k minus 1, right? But there's nothing special about n and k. We can do the same thing for n minus 1 and k minus 1, right? So we can replace this thing by a similar thing. So we'll have n minus 1 choose k minus 1 equals n minus 1 by k minus 1 times n minus 2 by k minus 2. And we keep on multiplying like this. So this will be n into n minus 1 by k into k minus 1 times n minus 2 choose k minus 2. And we repeat the same argument for n minus 2 and k minus 2, right? So we get n minus 1, n minus 2 divided by k minus 1, k minus 2 times n minus 3 choose k minus 3, right? And similarly we can proceed from 3 to 4 and so on. But we will have to stop at some point, right? And when do we stop? We stop when this k becomes 1, let's say. So in that case we'll have n minus 1, n minus k plus 2 by k minus 1, 2, and n minus k plus 1 choose 1. The number of ways of choosing one object from n minus k plus 1 objects will be n minus k plus 1, right? So this will turn out to be equal to n minus 1, n minus k plus 2, n minus k plus 1 divided by k minus 1, 2, and we can write it as 1, right? Doesn't make a difference. So you see that this is just the same formula we had before. But this argument provides some insight about the relations between these two quantities. So that's another way of looking at it. So now that we are done with the slide prerequisites, we'll start with the actual content of the lecture. So before we start, we'll recap a little bit about definitions of a function. Nothing too detailed, just the basic idea of what a function looks like. So suppose we have a set A and a set B. We'll assume finite sets throughout. So a function f a to b is a rule, and the rule does this. You pick an element a in here, and what the function will do is take a and send it to some element b here. And this a will only go to one b, so there can't be two arrows coming out of a, and there cannot be no arrow coming out from a. So there has to be exactly one arrow coming out from a, and that tells you the image of a. But this only assumes this on this side. So it may so happen that you have some a prime which also goes to this b. That is fine. We allow that. So arbitrary functions can look arbitrarily weird. So we will have arrows like this. So we can have any kinds of functions here, where you take any element, map it to any element. So it can so happen that all elements map to the same thing, no two elements map to the same thing. Not everything here needs to be covered, and there are lots of possibilities with this. But the basic idea is you take an element, map it somewhere. Now, we're not interested in all types of functions, but we'll look at specific types of functions. So we'll look at two special types: injective functions and surjective functions. So we'll recap about what these look like. Okay, let's do it there. So you look at a set A, at set B, you define a function. Now suppose for all the elements here, when you draw arrows, no two arrows have the same endpoint. So no two AIs map to the same thing. So you cannot have arrows like this, both meeting at the same place. You cannot allow that. So such types of functions we'll call injective functions. So one example of an injective function will be like this. So every car has a number plate to it. So you take cars, you map them into number plates. And no two cars are supposed to have the same number plates at least. So this is what injective functions look like. Surjective functions are slightly less obvious in definition. So the idea here is that, okay, not everything in B needs to be covered in injective functions or in general functions. In surjective functions, the idea is that everything in B needs to be covered by something. So you allow that two things go to the same thing, but you want everything in B to be covered by an arrow. So that is what surjective functions are. So for example, let's see, you have n as a set of natural numbers, 1, 2, so on, and 2n is the set of even natural numbers, 2, 4, 6, so on. Then the function f, which takes a number n to 2n, is surjective, because every even number is covered by this function. So that is one example. But for our main topic, our idea is to look at bijective functions. So bijective functions are functions which are both injective and surjective. And we'll see that while this sounds fancy, the content of this is really simple. So what it says is that you have a set A, you have a set B, and everything here maps to a unique thing here. Everything in B is covered, and no two arrows go same place. So what this says is that A is basically the same as B up to some rewriting. So if you can show that there is some bijective function between A and B, then A and B have the same number of elements. Because, so look at this. So you have A1, A2, A3, and you have, so A1 goes to something, let's call it B1, A2 will go to something different, B2, A3 will go to something different, B3. Now nothing else can be here, because otherwise subjectivity is violated, right? because that thing, suppose there's some b4, nothing goes to b4, but our function was bijective. So if you have a bijective function between two finite sets, they will have the same number of elements. So this is some of the machinery we'll use for our later constructs. Okay. So just to see some application of this notion, we'll look at one simple exercise. So suppose you have a function f from a to a. A is some finite set, let's say. And so what this does is it takes x to something, right? And let's call that something f of x now. This is just notation. So it takes x to something which we'll call f of x. Now, but this f of x is also in a, right? So f also takes f of x to something else. So there's something called f of x. So what we do is this: we look at set A, look at set A again, and look at set A again. So what we have is x going to something, that's something going to something else. So this thing we call f of x because we don't want to refer to it as some ambiguous thing, and this thing we call f of x. So the exercise asks that suppose f of x is equal to x. Suppose this happens for every x. The exercise asks us to prove that f is bijective. So the proof for that and this is as follows. First we see that surjective is obvious because look at this. A and A, you have a map f of f. So every x here, so every x in A, so everything here is covered by f of x because x is f of something. So every x here is covered by f of something. So f is surjective, that part is clear. But for f injective, what we'll do is some arguments. Suppose f of a equals f of b. Suppose a and b map to the same thing. Now, we'll apply f again. So we apply f on these. So if you apply f on two equal things, you'll obviously get equal things. But f of a is given to be a, and f of b is given to be b. So anytime two things go to the same thing, they have to be the same. Because we have shown that if f of a is f of b, we get a is b. So that is part of our argument here, and that solves the exercise. So we'll see that sometimes when we set up bijections, what we'll set is these types of functions. So then we don't have to always check that whether this is a bijection or not. We know that we can use this result and show that something we construct is a bijection. Okay. Now we move to actual combinatorial applications of these types of ideas. So so you have some tram tickets labeled from 000 to 999999. So all 6-digit numbers, including zeros everywhere. So 0 in the first digit is allowed. So all possible combinations of 6 digits. Now you call a ticket. So there are two types of tickets. One we'll call lucky. If when you look at it like this, A, B, C, D, E, F, the sum of the first 3 digits and sum of the last 3 digits is the same. So such types of tickets we'll call lucky tickets, and there will be several such tickets, right? For example, 111 this is a lucky ticket. 121211 this is a lucky ticket. So there will be many of these, and it's also not so easy to count all of these. It's by itself a good counting problem. And you'll also have some things called medium tickets. If you have A, B, C, D, E, F, and sum of all these 6 digits equals 27. So we'll call these medium tickets. The problem asks us to prove that, or not even prove, to find that, okay, call the number of these tickets as A, the number of these tickets as B. So the problem asks us to find A minus B. So you can do it by regular counting methods. So we can do something like this. We can count all possible lucky tickets and find A. We can find all possible medium tickets and count B, and then we can subtract and see whatever happens. But that takes a lot of time, right? That's cumbersome. But there's a neat bijection proof. So our claim is that this is in fact 0. So our claim is that A and B are the same number. No surprise there. Now, to show that, we'll construct, so we'll take a lucky ticket, something, we'll do an operation, we'll get, and we claim that we'll get medium tickets, and this is a bijection. So that will solve our problem. Suppose we start with A, B, C, D, E, F. Now, A, B, C, D, E, F, we map it to A, B, C, that's fine, but 9 minus D, 9 minus E, 9 minus F. So what we notice here is that for lucky tickets, A plus B plus C equals D plus E plus F. But here, if we add all digits, so it's A plus B plus C plus 9 minus D plus 9 minus E plus 9 minus F. So this minus D plus E plus F and A plus B plus C cancel out. So what we are left with is 27. So not only, so we have first shown that this map, which takes this tuple to another tuple, this map takes lucky tickets to medium tickets. First we have shown that. And we have shown that, okay, and now we'll show that A, this is injective, and B, this is surjective. And then we'll conclude that, okay, this set has same size as this set, and we'll be done. So first we show that this is injective, because it's easy and it's good to work out the details, at least at the start. So suppose there's another ticket, A prime, B prime, C prime, D prime, E prime, F prime, which maps to the same thing as this. Then this A goes to A and this A prime goes to A, right? So what we get is that A and A prime have to be the same for the images to be the same. Similarly, B and B prime have to be the same. Similarly, C and C prime have to be the same. Now for D and D prime, 9 minus D and 9 minus D prime have to be the same. So D and D prime have to be the same. Similarly, E and E prime have to be the same. F and F prime have to be the same. So then you get that if two things map to the same object, they'll have to be the same. So this is injectivity. Surjectivity is also this way. So what we do there is this. Instead of showing that this map covers all medium tickets, we'll just look at the reversal here and show that that is injective. So that will also be enough to prove the result. So we look at this. So we have A, B, C, D, E, F, which is medium. So the sum is 27. You change this to A, B, C, 9 minus D, 9 minus E, 9 minus F. And then since, okay, wait. Yeah, we don't even need to do that. Let's stop that. So what we'll do is this. When you compose this with itself, so 9 minus D again becomes D, 9 minus E again becomes E, 9 minus F again becomes F, and then you get the same thing back. So we'll use the involution idea. F of X is X idea. And we'll be able to get bijection. There'll be some details here, but I think the idea is this, so that's fine. So now we'll do some classical examples of this thing. And one such example, let's look at this. So we look at positive integers m and n, and we try to find solutions of x1 plus x2 plus xm equals n. So we try to find all possible tuples x1 comma xm. So we look at two numbers m and n. We try to write n as a sum of m positive integers. So xi's are greater or equals 1. And we try to find a number of solutions for this thing. So let's try it for m equals 2. So if you write n as a plus b, you have 1 comma n minus 1, 2 comma n minus 2, so on till n minus 1 comma 1. So there are n minus 1 ways of doing it, right? For 3 variables, you will have more cases because this will not necessarily be forced to be n minus 1. So it will be something which has some n minus 1, and so on for more variables. So when you increase the number of variables, it's not easy to just hand calculate everything. So we'll present an argument where we are able to count this. Like right now, we don't even know what the answer is. So our argument will be something like this. Since we are splitting n into m sums, what we can do is we can think of n as n blanks. So there are n blanks in total. Now, what an xi does is grabs the first few blanks. So suppose we write 12 as 3 plus 4 plus 5. What 3 here does is grab the first 3 blanks. What 4 does is grab the next 4 blanks. What 5 does is grabs the next 5 blanks. So the idea is this. We look at between these blanks, we insert dots. These are just for notation. So since there are n blanks and we are inserting dots between them, there will be n minus 1 dots. Right? And we have n minus 1 dots. And we realize that since we want to make m cuts in this thing, we want x1, x2, and so on, xm. So we'll get them like this, right? That x1 first block, x2 second block, and so on. So each block is determined by us chopping off a dot. So if I chop off this dot, then I will get x1 equals 1. If I instead chopped off this one, I would have gotten x1 equals 2. And and chopping off 1 dot will give you x1, for 2 dots will give you x2, for m minus 1 dots will give you xm minus 1, But the mth one is then automatically given to you, because whatever is left, you put that in xm. So in a sense, we have to take off m minus 1 of these dots from here. And turns out, okay, you look at any choice of m minus 1 of the dots. So you have n minus 1 dots and you choose any m minus 1. Yeah. 1, 2, n minus 1. Once you pick any m minus 1, then that automatically gives you one sum which sums to n. So we have constructed a bijection between all possible tuples that sum to m, n, and all possible choices of m minus 1 dots out of n minus 1. So this shows us that the number of such tuples is the number of ways of doing this. And the number of ways of picking m minus 1 objects out of n minus 1 objects is n minus 1 choose m minus 1, for which we already know the formula. So this is easy to evaluate now. Similarly, we can ask this question for whole number solutions. So instead of this condition, we make xi greater or equals 0, and we ask for solutions of this equation. So then, of course, the same argument doesn't work, because some of the xi's can just be blank. There can be, there need not be anything in there. So that gives us some trouble. So now we'll construct, okay, so look at a solution y1 plus ym equals n for yi greater or equals 0. We'll try to reduce this problem in terms of this problem. That is one of the key ideas when we are doing counting with bijections. We look at one problem and do some shifts and get another problem which is easier to count. So here we substitute xi equals yi plus 1. So any tuple, suppose we have 3, 4, 5 as a tuple, we take it to 4, 5, 6. And for these xi, the sum will be x1 plus xm equals n plus m. Similarly, any tuple here, since all xi's are greater or equals 1, any tuple here, when we subtract 1 from each coordinate, we'll get a valid tuple here. So we can see that there's a bijection between solutions of this with this condition and solutions of this with the condition xi greater or equals 1. But for this problem, we already know that the number of ways are m plus n minus 1. Choose m minus 1. So this helps us solve another similar problem to this. Okay. So let's try a counting problem, which is something we casually do when we see this kind of structure. So let's look at this. Not a good diagram. Okay, so let's look at this triangular grid. So you'll have, say, inside a triangular grid. Now in this, we want to count the number of parallelograms with points in here. So for example, this is a parallelogram because sides are parallel. This is a parallelogram because the sides are parallel. And this is a parallelogram because the sides are parallel. So there are many such parallelograms. And we try to count the number of such parallelograms in this triangular object. So there are solutions using some casework. So you can pick one parallel line, then vary the other and look at how many you get. Then you can look at other orientations. So there's solutions using casework, counting argument, but we'll present a neat argument here. So the neat argument is something like this. If you look at a parallelogram, it'll have one of three orientations: this, or this, or this. So parallelogram will either be like a diamond, like this, or like this. So there are three possible orientations, and because of the symmetry of the figure, for each orientation, there are an equal number of parallelograms. So if we count just this type of parallelograms and call this number A, then the number of such parallelograms will also have to be A, because the whole figure is symmetric. Like the triangle has symmetries on all three sides, and the number of such parallelograms will also be A. So the total number will be 3 times A, right? Because this type of parallelograms plus this type of parallelograms plus this type of parallelograms. So the harder part is to find what A is, and it's not clear how we count this, so let's do this. Suppose we look at a parallelogram here. In order to specify the 4 vertices of this parallelogram, it's enough to specify these 2 lines and these 2 lines, right? So we perform a clever trick here, because okay, so far these 4 lines, 2 of them can meet on this side, and then those intersection points coincide, so we are not in a good shape. So what we'll do is we extend this triangle by 1 and intersect these 2 pairs of parallel lines with this base side. The point is that these 4 points will have to be distinct, because these 2 points cannot be the same because these are different parallel lines. Similarly, these 2 points cannot be the same, and the closer ones cannot be the same because at best this vertex is here. So you can see that even if this vertex is here, these 2 will be on separate sides. So all these 4 points are distinct. So given a parallelogram of this orientation, we can map it to this quadruple. So every parallelogram, we start with the parallelogram and map it to these 4 points on this new line. But we can reverse the construction as well. So given any 4 points on this line, just pick the first 2 and draw parallel lines like this. Pick the last 2 and draw parallel lines like this. Whatever the intersections you get, that will also be a parallelogram. So the number of this orientation parallelograms is equal to the number of quadruples of 4 points here. And if you count the number of points in this newly introduced line, that will be n plus 2, right? Because we have n plus 1 points here, and we drew another line, we got n plus 2 points. So out of these n plus 2 points, choose any 4. And using this construction, you get a parallelogram and vice versa. So A is n plus 2, choose 4. And so the answer will be 3 times n plus 2, choose 4. So this, we know that since n choose 4 is big, this would have been difficult to count by casework by itself, because there will be lots of computation here. But this is a feasible way of calculating this. So for the moment, we pick a simpler example now. This was slightly tricky, this construction, but we'll pick a simpler example now. So we consider a lattice grid. So this is just fancy for integer points here. Points, 6 points. So this point is 6, 5. So suppose you're driving a car in this alley, and you're allowed to take only right turns and go up. So you're not allowed to go back or go down. So your paths can look like this, or your paths can look like, you cannot go down. So the goal is to find the number of paths from 0, 0 to this point. So in general, instead of 6, 5, let's talk about m, n. So the goal is to find the number of paths from 0, 0 to m, n going either right or up. So you can try playing with this because this is an interesting problem. But it's hard to count immediately, right? Because there's no real way you can characterize all such paths. So we look at the basic property of what a path looks like here. So each path, every time we take a turn, we either go right or we go up. So the path can be characterized as a sequence: R, U, U, R, U, 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 R, 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 U. So the point is, every time I tell you either R or U, you know where to turn. And any path, so given any path, we can map it to a sequence of R's and U's. Turns out that the reverse is also good. So if you have in an m plus n bit with m R's and n U's, any such m plus n bit will start from 0, 0, will have to end up at m, n, because the total right component is m and total up component is u. So you'll have to end up at m, n. Now from this string you have to pick m R's. So given an m plus n string, the moment you specify the R's, the u's have to be filled in just one way. There's no other way for the u's. Any questions? Okay. So from this m plus n string, you have to pick m R's, and the number of ways of doing so is m plus n choose m, right? Because this is a string, and we'll just pick m R's from here. So this problem, this idea is neat, but this problem by itself doesn't pose any difficulties. You have a lot of freedom. So we have a lot of freedom that any path we can map to R's and U's and R's and U's, and any such path happens to work for the general case. But we'll look at some variants of this problem where not every sequence will work and only some specialized sequences will satisfy this thing. Yes, now we look at the general Catalan paths problem. Suppose you have the same problem of going from 0, 0 to n, n. So in fact, this looks easier now because m and n are equal, so you don't have to worry. But the condition is that, look at this line. Your path is never supposed to cross this line like this. So your path is always to touch the line or stay below the line. You're not allowed to go above the line. So the question is, how many such paths are there from 0, 0 to n, n using only rights and ups, but without crossing this line? So for this, the bijection is very clever, and we'll try to construct that bijection here. If you look at it this way, 0, m, n, oh, n, n, sorry. It's easy to calculate the total number of paths. That is just 2n choose n, based on the previous exercise. Now, this is the total number of paths, but clearly not all of them work. Because if you look at just the path which goes up, at the very first step, we are doing something wrong. So instead of calculating the good paths, we look at the paths which do not satisfy our condition, and we'll call them bad paths. So we look at paths which cross this line at some point, and we'll calculate the number of such paths. And then clearly, from 2n choose n, we'll subtract that number, and we'll get the answer. So for the bad paths, the characteristic feature is that they always cross this line, but that is not very helpful. The interesting part here is that you look at the line which is just parallel and just above. So you look at the line y equals x plus 1. So a line just above this diagonal line, starting from 0, 1. The point is that any path that crosses this line, y equals x, will have to touch this line at least. It may still cross it, but it'll have to touch it. And the first time it touches this line, we stop there. So we look at a path, and suppose it touches this line here for the first time, and then it does whatever it wants. Now what we do is we look at this portion of the path, and we reflect it in the line y equals x plus 1. So this was a down thing, so this will be an up thing to a right thing, and so on. So we look at this portion of the path, and we reflect it in this y equals x plus 1 line. So 0, 0 reflects to minus 1, 1, and that is fine. And now this is a path from minus 1, if you ignore the original path, this reflected, okay, so call the original path P, this portion A, and the remaining portion B. So when we reflect A, we get A prime, and the path made by A prime and B in conjunction, that is some new path which starts from minus 1, 1 and goes to n, n. Now we'll do the other way around. So what we'll do is we'll start with a path from minus 1, 1 to n, n, and we'll reflect that. We'll do something to that path to get an original Catalan path or a bad path, because we are looking at paths that cross this. So this will be our map. We look at a bad path and we reflect it at the first intersection itself. We'll see that this first intersection idea is important. If we do it at any intersection, we'll run into counting issues. Or we can even do it at the last intersection, doesn't really matter. But yeah, the first assumption is important, and we'll see why. So we start with minus 1, 1, and you look at this line. The idea is that minus 1, 1 and n, n are on different sides of the line y equals x plus 1. So any path that goes from minus 1, 1 to n, n, this requires some argument, but intuitively it's obvious that it'll have to cross this line. Like, you cannot just keep on traveling in this region and reach n, n. So you'll have to cross this line. And so suppose we cross this line at the first point here, and then we do whatever we want. So the moment we make the first cross, we reflect this path back to the Catalan path. Now we'll show that this mapping is a bijection. So what we have done is, okay, if you look at a path P and a path P prime, on which we have done the same operation, and suppose we get the same path from minus 1, 1 to n, n. So if we get the same path, then first of all, the first intersection of these has to be the same, because otherwise the intersections itself won't match. So the images cannot be the same thing. Now, when we are first intersection for P and P prime match, the remainder of the path for both will be the same, so it would have been the same in P and P prime as well. And if you look at A prime, and for P prime if you get say A double prime, and those are the same, then when you reflect back, A and the portion of path of P prime till here will also be the same. So we see that if P and P prime are two paths that map to the same thing, then P and P prime have to be the same paths. We do it by breaking P in three parts: the first intersection, the part before it, the part after it. So when we are reflecting the part after it, we are not changing, and so for P prime also that part is the same. For P, for this intersection will have to be the same, because otherwise you see that the images cannot be the same, because images also will have this as the first intersection. And similarly, this portion is the same for both, so the reflected portion originally was also the same. So now we have proved that this is an injective map. Now we'll show that it's the other way around as well. So if we take any path from minus 1, 1 to n, n, and we do this operation of reflecting back from the first intersection with y equals x plus 1, then this path is a valid Catalan path, and any two paths from -1, 1 to m, n, n, if we do this operation and we get the same path, then those two must have been the same path from -1, 1 to n, n. So what we have shown is a bijection between the bad paths and the paths from -1, 1 to n, n using ordinary right and up moves. Now we shift, okay, so if you look at this, we have -1, 1, we have n, n. Any path here, we shift it like this. So n, n will go to n plus 1, n minus 1. No, wait, sorry. Okay, yeah. So if we change the coordinates from -1, 1 to n, n, we want to look at it as 0, 0 to something, something, right? So since we are translating this like this, we're adding 1 to the first coordinate and -1. Yes, that's fine. So all these paths from -1, 1 to n, n, by translating all of these paths down, we get paths from 0, 0 to n plus 1, n minus 1. So we are so this is also a bijection between these paths and this paths. And for this, by the m, n argument, we know that the answer will be 2n, choose n plus 1. So this 2n choose n plus 1 is the number of bad paths, and the total number of paths is 2n choose n. So the total number of good paths is 2n choose n minus 2n choose n plus 1. And this is the answer to the problem. If we dig a little deep and do the algebraic calculations for this. Yes. Oh, so sorry, I didn't get your question. Yes. Yeah. Yeah. Yes, yes, yes. That's fine. Yeah. Yeah, because those two configurations will turn out to be the symmetric thing along the diagonal. Yeah, that's true. So if you do a little bit of algebra, this will turn out to be 1 over n plus 1 times 2n choose n. So these numbers, these are called Catalan numbers, and these have some significance in other counting problems as well. So there are many theorems which base the counting based on Cn as the constants. So Catalan paths are one example of this type of argument. Now we'll make a digression and discuss one more type of objects before the end of the lecture, which is totally different from this, but the idea of counting with bijections is the same. So we'll see that the idea is quite versatile in nature. So let's look at the idea of partitions. So we saw something slightly similar to this. So the idea is we look at n, so any number, and we write it as a sum of numbers a1 plus a2 plus ar, r greater than 0. Now with the condition that a1 greater equals a2 greater equals ar, and we look at all possible ways of writing n in this form. So we list down all those ways and we get some yeah, and we are allowed to change r. So r is not fixed. R can be 1 for some case, 2 for some other case. R is not fixed here. So what we get is the partition number of partitions of n. We'll call it P of n for now. So it turns out that there are no good explicit formulas for P of n. So you cannot write it as n into n minus 1 by 2 or something like that. There are no good formulas associated to this. So instead of finding formulas, we can find equivalences. Whether counting something of this type is equivalent to counting something of another type. And then we can see that there's some similarity between those things. So we'll sketch one such problem. So the problem is, so let n and k be natural numbers. We look at number of partitions of n with exactly k parts. And so this is one thing, one type of object. We'll call this number as A. And then we look at B, number of partitions of n with largest part equal to k. So our goal is to show that A and B are equal. So on the face of it, this is hard, right? If there was some explicit formula for any of these things, we can just do the algebra and check whether the equality holds here or not. But we don't know any formula for P of n. And even with knowing a formula, it will be hard to do the actual calculation. So we'll do some clever argument here. So what we'll do is, we look at a visualization of what a partition looks like. Suppose we write 12 as 5 plus 4 plus 3. So we'll think of it as 5 dots here, 4 dots here, and 3 dots here. If we write 12 as 6 plus 3 plus 2 plus 1, then we'll think of it as 6 dots on the first row, 3 dots on the second, 2 dots on the third, 1 dot on the last. So we can look at it as like some dot graphs where the ith row has ai dots. So we can look at it as this triangular kind of object with the ith row having ai dots. And so a partition for n corresponds to one such diagram. So these are called Ferro diagrams. So a partition of n corresponds to one such diagram with exactly n dots. Correspond to That's clear, right? Because n dots will correspond. So each of these are the parts and n is the sum. So now we try to visualize what each of A and B look like. So A says partition n with exactly k parts. So the number of parts is the number of rows. So A says that, okay, you are allowed to partition n, but you have to keep k rows. And B says that the largest part equals to k. So you're allowed to partition this, but you have to keep k columns. So we see that there's already some kind of symmetry here. That in one situation you have k rows, and in another situation you have k columns. So the idea is that we do a row column shift. So what we'll do is, we'll look at a triangle. This is not the correct pictorial thing for this, but we'll look at this as the model. So we have k rows here. Now we rotate it like this. So we have k rows here, and oh, not like this. Yes. So yeah. So we rotate it like this. So we have k rows here, and then we reflect it along the central line. So then we'll have this. So anything with k rows like this, we map it to. We first flip it like this, and we get k rows on the top, but this is like inverted. So we switch it along this axis, flip it like this, and we get k columns. So k columns and whatever number of rows. So this operation of taking one such diagram of these dots and rotating it like this and flipping along the y-axis, so that gives us an equivalence between a correspondence between A and B, and we can check that this correspondence will be a bijection, because with each row, if we have some dots here and suppose another thing maps over there, then we'll have that number of dots. So this has, say, x dots, this also have x dots, and suppose something else maps to this, then that too has x dots here. So originally it was supposed to have x dots, and so this gives us a correspondence between Farad diagrams with exactly k rows versus Farad diagrams with exactly k columns. So that is one kind of one way of proving this result. So is that fine? So the main idea here is that once we visualize this as a triangular diagram, we can perform operations with the diagram itself. And because of the geometry of this thing, we are motivated to consider rotations and then do some kind of symmetry, because we know that this corresponds to having k rows and this corresponds to having k columns. So the idea is that somehow just interchange the rows and columns. So I think we have time for one more example. Yeah, so let's discuss this example, which is slightly hard. So is that fine? So it says that, okay, we are still looking at ideas like partition. So we'll look at partitions of n, A, R, but this time we don't allow equality between the parts. So they are strictly greater and R is greater than 0. So this is our A, the number of such partitions of n where the parts are distinct. And our B is number of partitions of n such that AIs are odd numbers. So these two look completely unrelated structures. On the one hand, we have distinct parts. On the other hand, we have partition into odd summands. But turns out that these two numbers are also equal. So this is rather surprising, because we don't really expect partition into odd parts to have connections with partitions into distinct parts. But we'll see that, and this is also the case. And this will also show that it's helpful to look at different styles of bijection. So earlier we looked at Farad diagrams. Now we'll look at something which has a more numerical, number theoretic style flavor to it. So what we'll do is we'll try to construct from distinct parts to odd parts. Odd parts. So we'll try to construct one map from these to these. And the idea there is this. Suppose you have any part which is of the form, so any part is some natural number, right? And natural numbers are natural numbers will have some powers of 2 dividing it, some 2 power k times m. This is what all natural numbers look like, right? K is allowed to be 0. So if it is an odd number, say it's 17, then m is allowed to be 17 and k is 0. If it's 18, I can write it as 2 times n. And in general, for any natural number, I can write it as 2 power k times m. So every summand here will write ai as bi times 2 power ci. And bi's are odd. So this automatically suggests what we have to do here. So we can write ai as bi plus bi plus bi 2 to the ci times. This is how multiplication is defined, right? And each of these is an odd number. So when we accumulate this sum for I equals 1 through r, we'll get loads of b1s, loads of b2s, and so on. And then we'll rearrange them in increasing order. So of course we'll have many multiplicities, but the point is that each of these parts are now odd parts. And they can be the same. So this is, and it's easy to see that this map is injective, because so each of these bi's will have some multiplicity going on. And suppose this bi also occurs from a1 and also occurs from ar, then its representation will have 2 power ci and 2 power c1 and 2 power c2. So if bi is what we get from a1 and also what we get from ar, then it will have 2 power c1 plus 2 power cr. But because a1 is bigger than ar, c1 is bigger than cr. So we look at this in the binary representation. So I guess you're familiar that we can write natural numbers in base 10. Suppose 987 is 9 into 100 square plus 8 into 10 plus 7 into 10 power 0. So 10 here is nothing special. We can do it for 2 as well. And in 2, every natural number looks like 2 power x1 plus 2 power x2 plus 2 power xs, x1 greater than x2 greater than so on. And turns out that these representations are unique. For example, in decimal system, we see that the representations are unique. So even in binary system, it's not surprising that the representations will be unique. Like there's nothing special about 2 and 10. So here when we look at bi's coefficient, we'll see that we will be able to separate c1 and cr. So even if bi occurs from multiple sources, so even if bi comes from a1, a2, a7 and all that, we'll still be able to filter out what exactly was the part a1. So this tells us that this map is injective, because if you have some other partition which leads to the same form, then you can just filter out the bi's, look at the coefficients, and each of the exponents of 2 will tell you what the ai's were. And there's like a unique way from going through these bi's to the ai's. And that will tell you that the map is a bijection. That is an injection. Now we'll go from odd parts to distinct parts. Yes, so since we are allowing equality here, it may so happen that some part occurs k times. So let's say b is a part and b occurs k times. And suppose k can be written as 2 power k1 plus 2 power k2 plus 2 power kj. k1 greater than k2 kj. This is possible because any natural number, we are assuming the binary representation as a fact, that any natural number has this kind of a form. Suppose b occurs with this multiplicity, so bk is 2 power k1 b plus 2 power k2 b plus 2 power kj b. Right? So when you are writing n as a sum like this, we look at 2 power k1b. This is strictly bigger than 2 power k2b and so on till 2 power kjb. So all these are distinct parts. But if we had another source, so b was one odd number, if c was another odd number with l, and suppose we got something like 2 power l1 c, this number cannot be equal to any of these because the odd parts are different. B and c are different. So if we have 3 into 2 power something, say 100, and 7 into 2 power 98, these two things cannot be the same, not because we will actually check them, but because the odd part here is 3 and odd part here is 7, right? So you cannot have that. If they're equal, then each of the parts in the factorization will have to be the same. So all these numbers we get 2 power k1b and so on, and similarly 2 power l1c from a different c, we look at all these numbers and we sort them. So we look at the increasing order, and that gives us a unique partition of n into distinct parts. So from odd parts we can go back to distinct parts, and similarly we can look and check that this is also an injection. So we have established an injective function both ways, and so this will be a bijection. So that was the idea for this problem, and I think that's all for today's lecture. So thank you all for coming.
So that's it for today, and this is the last S.T.E.M.S lecture. We'd like to remind the audience again that the exam happens on 12th and 13th of January 2019. You can register online for the exam from the website of Tessellate. And with this, we conclude the S.T.E.M.S lecture series. Hope you all enjoyed it, and we wish you good luck in life. Thank you.
Did you like this lecture series? Check out Brilliant's courses, which have a lot of material that will help you prepare.